Hello dear friends, we continue our discussion on heuristic algorithms. In the previous lecture we have made some examples of construction heuristics, and in this video lecture we will make more examples on construction heuristics. I will try to show you how different uh, real life restrictions may result in modifications in the solutions and the heuristics. And we will talk about the solution encoding, which is in fact the representation of solutions. Okay? So let's get started. With a few examples, I want to show you how some additional restrictions on the problem definitions may affect our algorithms. So how we can modify our algorithms to account for different restrictions. For this purpose, I'm going to consider the knapsack problem. We already solved this knapsack problem, and if you remember in the basic definition of knapsack problem, we have a certain number of items. In this example, we have 10 items. Each of them have their own benefits, utilities, and their sizes. And we have a knapsack with a certain capacity. In this example, the capacity is 210. And we want to select, this is a 0,1 knapsack. So we want to select a subset of items without exceeding this capacity, and with the objective of maximizing the total utility. And remember in our previous lecture we considered three alternative constructive heuristics. Now I'm considering the third alternative, in which we were calculating a ratio of value to size. So for this first item, the value to size ratio is 0.93. And then we are sorting these items with respect to their ratios in decreasing order. So the largest ratio, the highest ratio is item 2. So it's sorted as in the first place. And then we have item 5 in the second place, and etc. Okay. Now, if we don't have this restriction, so in this example we have a restriction, because in real life we may have such restrictions. Okay, so in this example we have a restriction stating that item 2 and item 10 cannot be selected at the same time. Okay, now I want to see its effect of this restriction on the solution as well as on the algorithm, how we can modify the algorithm according to this. Okay, so if we don't have this restriction, basically we were following these steps. Basically, we were setting a variable value equal to 1, and then we were checking the capacity of the knapsack. If the capacity is not exceeded, we continue with the next item, but if it is exceeded, then we revert the variable back. We don't select that variable, and we continue. We don't select that item, and we continue with the next item. But when we have this restriction, now in our algorithm we need to include a control. Okay, it means that we are including one more step. And in this step, what we do, so in the main loop, for I equals 1 to 10, which means that for each one of the 10 items, we are repeating these steps. Okay. The control says that if the considered item is 2, so when we set this item number to some thing, if it is item 2, and if item 10 is already selected before this item 2, what does it mean? It means that according to this restriction, we cannot select item 2 anymore. Or if we are currently considering item 10, and item 2 is already selected. In this case, we cannot select item 10 anymore. So it means that if we are in this case, we cannot continue with the remaining cases. We cannot set the variable value to 1 for these. So basically what we do, we increase our index by 1 and return back to the beginning of this step to account or to continue with a different item. Okay, so basically this restriction appeared to be a new control in my heuristic. Now let's solve the same problem with this additional restriction and with this additional step. So basically we start from the ordered list. Since this is the first item in the ordered list, we set its variable value equal to 1. Okay, and then since its size is 26, we check the capacity. So we check 210 minus 26. Okay, 210 minus 26, we have 184. Okay, since we still have remaining capacity, we continue. So we return back to the beginning of step 3 to increase I to 2. It means that we are selecting the next item. Okay, this is item number 5. Look, item number 5. And item number 5 means that it is not item 2 or 10. So it means that we don't control this step here, and we move directly to here. And we make its variable value equal to 1. And then we check what happened to the capacity. So 184 minus the size of this new item, which is 22, it's 162. So we are we have enough capacity, and we return back to the beginning of the step. And in the third item, okay, so this one, it's item 10. Okay, it is item 10. Now we need to check this one. If considered item is 2, no, considered item is not 2. Or if considered item is 10, yes, considered item is 10. And if item 2 is already selected, and when we look, the first item that we selected was item 2. So it means that item 2 is already selected because its variable value is 1. Is already selected. So what do? We cannot place this item 10 into our knapsack, so its variable value will be 0, and we move to the next one. We return back to the beginning, and we continue with the fourth order, which is item 3. So item 3 is not 2 or 10, which means that we increase its variable value to 1, and then we check for the capacity. So 162 minus 48, we have 114, and we have remaining capacity. So we continue with the next item, which is 5. So we increase its variable value to 1, and 114 minus 85, the remaining capacity is 29. Okay, and we still have a remaining capacity. We continue with item 6, but item 6 size is 95, which is larger than 29. We cannot take it. We continue with the next one, item 7, 45, again larger than my remaining capacity. I cannot take it. So 8, its capacity size is 21, so I can increase its value to 1, and the remaining capacity will be 8. And we continue with the ninth part. Since its capacity size is 55, we cannot take it, and we continue with the 10th item, which is item 7, and its size is larger than my remaining capacity, so it's 0. So it means that with the addition of this restriction, we selected this item 1 with a utility of 79, and then we selected item 2 with a utility of 32. Then we selected item 3 with a utility of 47. Okay, and we selected item 4 with a utility of 18. And we selected item 5 with a utility of 26. And in total, our objective function value is 202. Okay, so this is the solution at the end. If you remember our previous solution without this restriction, I believe it was 204. And with the addition of this new restriction, it reduced to 202 because an additional restriction will not make the objective function value better. It can either stay the same or be worse. But the thing is, what I want you to see here is when you have additional restrictions on the problem, these additional restrictions are usually lead to new checks, new controls, or new steps in your heuristic algorithm. And this is how you can modify your algorithm according to this. Of course, if the restriction is something special, something different, you may need to have a different alternative. Maybe the original algorithm will not be able to solve the problem anymore, and you will need an additional or a totally new algorithm. Okay, now let's consider a similar example. Again, we solved this example, which was the single machine scheduling problem with total completion time. But in this case, we modified the problem. We have a new restriction which says that the jobs that we need to process has ready times, and these ready or release times are given with this parameter. So remember, if this ready times were not given, then we were using this simple rule, which was so-called shortest processing time algorithm. And in fact, we said that for this problem, SPT algorithm was an exact algorithm. It is not a heuristic, but it provides the optimum solution. It guarantees the optimum solution. But when we have these ready times, let's see how this algorithm performs. Okay, so let's use, without any modification, let's use the same algorithm. And according to this, if we use this SPT heuristic, we see that the shortest processing time is this job 1, so it will be in the first order. Then job 3, sorry. Job 1 and job 5 have the same, so we can select one of them randomly. Last time we selected job 5 as the second, in the second place, and job 1 in the third place. Then job 4 will be in the fourth place, and job 2 will be in the fifth place according to the shortest processing time. Let's sketch the Gantt chart and see and calculate the total completion time. Look, in fact, in this problem, we are sequencing the jobs, okay? But when we have this sequence, then we need some algorithm or some method or some function to calculate the objective function value. This sequence by itself does not provide me the objective function value. I need to calculate the objective function value. And the easiest method to do this is to sketch the Gantt chart. Again, let this be our timeline. Okay, and this is time, let's say 0 here, and we start with job 3, and okay, job 3 has a processing time of 3 units, 3 minutes, let's say, but at time 0, job 3 is not ready. It will be available after time 5. So which means that I can only start job 3 after time 5. And it will have a processing time of 3 units. So it will from 5 to 8 it will go. This is job 3. Okay, so what will happen during this time? During this time the machine will wait idle. And you can say, but why there are some parts, for example, part job 1 and job 5, when they are ready at time 0. So let's continue with them. Yes, of course, that's an idea and it will be a solution, but it is not the SPT heuristic. The SPT heuristic orders the jobs in this way, and you need to use this sequence according to SPT, which starts with 3. And in order to start with 3, the machine should be idle until its ready time. Okay, after that we have job 5, which is already arrived at time 0. So we can just immediately start job 5 and it will end at time 13. And then we will have job 1, it will go up to 18. And then we will have job 4. Okay, it has a processing time of 7, it will go to 25. And then we will have job 2. Okay, by the way, at each time, of course, you need to check if that part is ready or not. So at this time, when we are starting job 4, we see that its ready time is 6, so it's already arrived. We can immediately start. And here, we are starting job 2, and we see that its release time is time 20. It means that job 2 is already arrived, and we can start immediately, and its processing time is 12 units, so it will go up to 37. So the total completion time will be this 5 plus 8 plus 13 plus 18 plus 25 plus 37. So let me calculate 13, 18 and 25 and 37, which is 106. So the total completion time of this solution is 106. But in fact, you can immediately see a better solution than this one. How? So this job 5, it has a processing time of 5 time units and its ready time is 0. It means that if I move this job 5 to the first sequence, it can start at time 0 and finish at time 5, and none of the other jobs will be late if I do this, because job 3 will still start at time 5. Okay, so now let's consider this schedule instead of the previous SPT rule. Now let's consider the order: first 5, then 3, then 1, then 4, and then 2. Okay, so again, let's sketch the timeline. And we will immediately start with job 5 until time 5. Then we will proceed to job 3 because it arrives at time 5, and it will be finished at time 8. And then we will continue with job 1, which is already arrived, and it will be finished at time 13. And then we will move to job 4, which is arrived at time 6. So we are ready to process it. So this is job 4, and it will go until 20. And at time 20, we can see that job 2 is arrived just at this time, so we can start processing it, and it goes up to 32. And you see the completion time of the last job is earlier, but also let's check the total completion time, which is the sum of this. Be careful, total completion time is different than the make span. So the make span of this schedule is this make span, which is the completion time of processing of the last job. Okay, the make span of this sequence or of this solution is this. But total completion is the sum of individual completion times of the jobs. Okay, not only the last job, but the completion times of individual jobs. So it will be in this example 20 and 32, it will be 78. Okay, the total completion time is 78. Okay, so remember, if we don't have the ready times, the SPT heuristic was an exact algorithm. It was providing the exact solution. But when we include the ready times, now this SPT heuristic is not, SPT algorithm is not an exact algorithm. In fact, it may provide a bad solution. Okay, so it becomes a heuristic, and somehow we may need to include these ready times into the problem. So how can we modify this algorithm? There may be many modifications. Of course, you can think your modification as well. So we can write a heuristic, just an idea. Let me write here. Okay, so as the step 1, I'm saying, okay, find the job with the earliest ready time. Okay, but of course, for example, when you look at this example, the ready time of job 1 is 0 and the ready time of job 5 is 0. Both of them are 0. Which one should I select? So I need to include if there are multiple jobs with the same ready time, okay, select the job with shorter or shortest, let me say, processing time. Okay, this is the first step. And then second step, for each remaining job, so select the job with the shortest processing time and assign to first sequence. So this will be the first job. Then for each remaining job, I'm going to do this. I'm going to follow these steps. When the previous job is completed, okay, so from the jobs which are not scheduled yet and which are ready, okay, select the job with the shortest processing time. Select the job, or let me write like this. Select the unscheduled job with shortest processing time Okay, among the jobs that are ready. Okay, so we will start with the first job. We will find the first job, and then when it's completed, at that time we will look at which jobs are ready, and we will determine or we will select the next job as the job with the shortest processing time and which is ready at that time. We may include some more details here because when a job is completed, maybe there are no ready jobs at that time, but still there are some unscheduled jobs. So a number of jobs may be the case that they will arrive later on. So we will say that if there are unscheduled jobs and which are not ready. Okay, so set the time to the shortest ready time of these jobs. Okay, so this is in fact this situation. Let's assume that you scheduled one job here and it's completed here, and then among the jobs which are ready at this time, you scheduled another job here, and now it is time here, and there are some more jobs, but none of those jobs are ready at this time. So what you will do, you cannot say that, okay, the schedule is complete and stop. You have to wait until the arrival time of the earliest job, and then we will continue with that one. Okay. So let's try to solve this problem with this heuristic which we just developed here. Okay, it's just an idea. We don't know if it is a good one or not, but it has some idea. Okay, according to step 1, again, let this be our timeline, this black line. Okay, and this is time 0, let's say. So according to the first step, the earliest ready time is either job 1 or job 5. And then if there are multiple jobs, it says that select the one with the shortest processing time. So they both have the same processing time. So we need to select one of them, either 5 or 1. It doesn't matter. I will start from 1 this time. Okay. So let's say that this is job 1, which goes from 0 to 5. And then we are currently at time 5. And which jobs are ready at time 5? So we already scheduled job 1, and at time 5 we have job 3 and we have job 5. And what shall we do? According to this step here, we will select the one with the shortest processing time, which is job 3. Okay, so now we are scheduling job 3 here with a processing time of 3 that goes to 8. Now the current time is 8, and I need to look at all the jobs that are ready at time 8. So job 4 is arrived at time 6, job 5 is arrived at time 0, so these are ready. Job 2 is still not ready, and the shortest processing time among these is job 5. So we are selecting job 5 and go until 13. Okay, then we are at time 13 and only available job at this time is job 4. It means that we need to continue with job 4 until 20. and at time 20 this job arrives. We already scheduled job 4, so we schedule job 2 here, and which ends at time 32, and this is in fact the same solution which we found in the previous case. Not the same solution because the positions of job 1 and job 5 were different, but if you change their position you will get exactly the same objective function value, which means that these two solutions are alternative optima. Okay, so you see, with the addition of a new restriction, we need to modify the heuristic, and that heuristic, the previous heuristic may be a bad heuristic with the addition of the new restriction. Even an exact algorithm may become a poor heuristic with those additions, but we may modify the algorithms. We may develop an new heuristic for to account for this new restriction. Okay. Now I want to talk about an important property or important aspect of these heuristic algorithms. That's called solution encoding. In fact, this encoding means how do we represent the solutions? Okay. How, for example, if you are going to explain a solution to someone else, what will you say? How will you report the solution to someone else? That's important. In fact, in the solution encoding in heuristic, when we are talking about heuristics, you should always keep in mind that we are writing these heuristics for computers. We need to code it in the computers, and the computers will follow all those steps. And when we say this solution encoding and solution representation, in fact, you need to think about, okay, how can I describe this solution to the computer? Because computers know about numerical characters, okay? So you either can give a numerical value or a vector of values or an array of values, okay? So it should be suitable for the data structure of the computers. The coding, the encoding of the solution or the representation of the solution should be suitable for the computer. So you cannot give a shape to the computer. It can be a matrix, it can be a table, but you cannot give a figure as a solution. Okay. So let's consider some examples and try to see different types of encodings and what are their advantages and disadvantages. Again, the knapsack problem. Let's start with the knapsack problem. The encoding of knapsack problem is usually straightforward. Okay? What do we do? In the previous example that we considered, if you assume, we had 10 items. So in order to represent the solution of a knapsack in a computer, we define a vector, okay, with 10 spaces, vector of 10 elements. And this vector of 10 elements, I can represent it like this. Okay, they are all either 0 or 1. Okay, so the first item, the first element of this vector, if it is 1, it means that we are selecting item 1. If the second one is 0, we are not selecting. If the third one is 0, we are not selecting. Fourth one, fifth one, and etc. So we need to have a vector of 10 spaces. And in fact, you don't need to have this parentheses, you don't need to have this comma and etc. You can just represent the solution as a sequence of zeros and ones. 1, 0, 0, 1, and etc. And this is just the representation of the solution. And it's a pretty good representation because when we are talking about this encoding and representation, later on we will talk about the search algorithms and we will make search given a solution, we will find some neighboring solutions. We will define what's a neighborhood. In meta-heuristics, for example, in genetic algorithms, we will talk about crossovers and mutations. So your solution representation should be suitable for all these crossovers, mutations, and finding neighborhood, and etc. On the other hand, these solutions are kept in the memory of the computers. And especially for large size complex problems, the computers will spend a lot of CPU time and CPU, and a lot of memory will be allocated. So it means that if your solution representation is unnecessarily large, the computer may be out of memory, or it will be extremely slow. So it means that you need to keep this representation as small as possible. But as I said, for knapsack problem, this representation is pretty straightforward, and it's very suitable for finding neighboring solutions, or for mutations and crossovers and all those operators. We will talk later on. Let's move to a different story, which is the traveling salesman problem. Okay, in TSP we are trying to find the tour of cities. Okay, if we assume there are 5 cities or 6 cities, we want to find an order, and we can represent this order, for example, like this: 1, 2, 5, 4, 6, 3. Okay, so if I tell you these are the order of the cities, then what does it mean? It means we start from city 1 and then go to city 2, to 5, to 4, to 6, to 3, and then we return back to 1. And since this is a tour, which means that we are returning back to 1, in fact, the starting point is not important. Since it is a tour, since it is a circle, what is the starting point of a circle? Did you start from here, or from here, or from here? It doesn't matter, right? So we can represent the solution with the ordering of the cities in this way. It's possible. But you see, when you compare this representation with the previous one, the previous representation is directly related with the mathematical model of knapsack, because in knapsack we have a decision variable xj, which is 0 or 1, and if we select item j, then it takes the value of 1, otherwise it is 0. And the solution basically represents the vector of these variables. But in TSP, in the formulation of TSP, what was our decision variable in mathematical model? So it was two-dimensional variable xij. It takes the value of 1 if the tour, let's say, goes from city I to j, and 0 otherwise. But in this representation, we don't have anything to do with this decision variable. Of course, having this representation, having this solution, you can find the corresponding xij values. Okay, so it's easy. For example, according to this, x12 is equal to 1 because we are going from 1 to 2. x25 is equal to 1. x54 is equal to 1, and etc. And all others are 0. But again, the solution is not represented with 0 and 1s with a vector. But still, it's also possible to represent a solution using these decision variables. And how do we do it? In fact, this time, instead of a vector, you need to use an array. Okay? And in this array, it should be, if you have n cities, it should be n by n. Okay? And what does it mean? So this point here represents x11. Okay, if this is 0, according to this solution, okay, let me write 1, 2, 3, 4, 5, 6 cities. 1, 2, 3, 4, 5, 6 cities. Okay, we are going from 1 to 2 according to this solution. So this is 1 and all others should be 0. Then from 2 we are going to 5. It means that all others are 0, but this is 1. Then from 5, from 3 we are going to 1. So 3 to 1, all others are 0. Then 4 to 6, it means that all these are 0 and this 6. And 5 to 4, this is 4. And 6 to 3, so this is 1. This is the representation of the same solution with this one. The first one just uses the ordering of the cities. The second one uses the values of the decision variables. Which one is better? Of course, it depends. It depends what kind of algorithm do you have and etc. But there are some basic advantages and disadvantages. According to this first representation, if we just use the ordering of the cities, the size of the vector that we are keeping in the memory of the computer is just n, the size of the problem. Okay, so the size of this one is just n. On the other hand, the size of this table that we are keeping is in memory is n by n, which is n square. So it means that you are using memory more in the second representation. And if you check the second representation, you also immediately see that most of the elements, most of the entries of this table are is 0. Okay? Only a few of them are ones. It means that you are keeping many zeros and they are useless. Okay? With this, from this representation, as I said, you can immediately shift to this representation. It's also easy. And later on, when we see the neighboring and for example, in genetic algorithms, we talk about the crossover operations. Making crossover in such a representation, table representation, may be difficult because be careful in this representation when you check the row sums, so you have only one entry which is greater than 1 at each row, okay, and also at each column you have only one. You need to have, because these are the basic constraints of TSP. Otherwise, either you have an infeasible solution or you have a subtour. Okay, so this representation, usually for TSP problem, the representation of the solution is as the ordering of the cities. When we come to the machine scheduling, again we have a similar issue with TSP. Remember the previous example. We represent the solution as the order of the jobs. So the fifth job comes first, then the third job, then job 1 and 4 and 2. Okay, and this is very similar to the TSP. Okay, instead of ordering of the cities, we have the ordering of the jobs. The basic difference is in TSP, after 2, we assume that we are moving back to 5. But in machine scheduling, there's nothing like this. At the end of this job 2, the schedule is completed. So this is the starting point, this is the ending point. It is not a tour. And there's no subtour constraints in machine scheduling. If you want to represent the solution using the mathematical model, again you need to consider what was your decision variable. And again, we formulated the same problem in different ways, but one of the formulations, the decision variable was this. Xij is 1 if job I is assigned to position j, okay, and 0 otherwise. And again, since we have 5 jobs, we have 5 positions. It means that if you want to represent the solution, again you need to represent it as a matrix of 5 by 5. And again you will have zeros and ones in this representation. And the same arguments, same advantage and disadvantage that we have for the TSP is valid for the machine scheduling as well. Okay, so these are some basic representations of solutions, and as we proceed with the improvement algorithms and with meta heuristics, we will see other representations. So for the set covering problem, please try to represent the solutions by yourself. Try to find or suggest some representations of solutions by yourself. Okay, it's an exercise for you.